Good morning. Start the morning off today talking about process technology limbo. In essence, this talk is going to follow on from the talk I gave last year, where last year, to give you a little recap, talking about the current node set that we're in, the lithography cost of scaling is really getting out of hand, with or without EUV. And in order to kind of manage it, we've been doing a lot of tricks under the hood, using the FinFETs to make stronger fins, but fewer of them to shrink our logic, and then doing a lot of one-time tricks to increase transistor density. In fact, interestingly, one of the topics I mentioned last year showed up in the Intel 10 nanometer process this year. That was with a feat of process engineering. They were able to move the gate contact over the active devices and shrink the footprint with no pitch, get an area savings. Now, with all the tools that we know about, we can foresee 7, 5, 3, possibly, with what we know. But then we don't. So that's the term limbo that I'm using. I want to look a little bit further out this year and talk about this idea that we know big change is coming. There's a lot of options. We're not sure what. But that does get us into this term limbo. Now, if you're thinking the religious term, things aren't that bad. We haven't found ourselves in a dark place we're never going to get out of. There's a lot of interesting options. And also, important note, if based on the title of this talk, you came in thinking that anything like this was going to happen on the stage, I'm sorry to disappoint you. I'm actually going to talk about this third definition of limbo, this transitional intermediate state where we can see the end of the normal way of pitch scaling MOSFETs, and we know there's some strange stuff out there we might have to jump to. And so to kick off the talk, I want to talk about a couple things we know pretty well are coming along in the roadmaps. One is new non-volatile memories, and the other is various forms of three-dimensional integrated circuits. Now, last year I talked about the kind of conventional 3D IC, which I call 3D stacked IC, or SIC. That's your interposers, your normal kind of TSVs, high bandwidth memory. We've seen high-end products come out that definitely show the benefit of this kind of technology in power and performance. And we have every right to assume that that will mature and expand into the broader market. But as I mentioned, I want to talk further out. And there are a couple other 3D IC terms and technologies that I want to talk about going forward. And to do that, I'm going to have to bring up an uncomfortable subject, first of all. And that's the fact that most of us in this room, we're, of course, focused on phones. They drive a lot of our technology. But most of us in this room are working on priority number 6 of a phone, according to one person's opinion here. But if we go up to number 3, the camera, some interesting stuff is happening there. The pressure to make ever-increasingly amazing cameras has driven the photosensor industry to really aggressively push this wafer-bonded 3D IC. And when you think about TSVs in the normal sense, they're 50 micron, 30 micron pitch. You can see the pitch of these things are much smaller than that. And also because of the cost pressure, this is a wafer level process, so it's a lot cheaper than a chip level process. This is a chip announced by Sony this year. It's 3 layers. They're very different functions, the image sensor, buffer memory, and the processor that get you these amazing 1,000 frame per second cameras that are coming out. Also, it allows them to mix and match the technologies for each layer. That's another cost optimization step. But what's interesting is this has then brought forth tools and processes that are fairly capable. And the roadmap for image sensors is to get to a per pixel interconnect. That's about a micron pitch. What's interesting about that is if we can, in the logic space, piggyback onto this technology that's going forward so fast, I think good things can happen. There's a paper study I've shown here from us and Georgia Tech this year, where we hypothetically looked at if you could do a 1 micron pitch kind of interconnect, just logic folding, just logic critical path folding in an ARM core, we can get a whole Moore's law of performance out of that easily. And that's not memory folding, memory stacking over logic. There's a lot of really interesting things to do that have even more promise. But that brings up another aspect of the technology limbo that I believe we're going to see more and more going forward. And that is that to really take advantage of, say, a high-density interconnect like we're talking about, you have to comprehend and adapt your architecture to take advantage of something like really, really lots of close memory. But you can't do that unless it's properly abstracted up into that level, or normal design flows. Yet this kind of real 3D IC breaks every kind of design tool that would allow us to do our normal work. So this is kind of an example of this theme of limbo, where a lot of cool technologies are coming along. They don't look like MOSFETs. They don't look like von Neumann. And we have to do a lot of work to really vet them and understand what is going to give us the best advantage. I'll be talking about that more later. So there's one more type of 3D IC technology down in the transistors I'd like to talk about. And I want to go all the way back 5 years ago. This is a talk I gave here, fretting about how hard it would be to design with FinFETs. And here we are in 2017. We can already see that 5 nanometers, probably 3 nanometers is the end of the FinFET era. It just can't go that much farther. And the most likely candidate now looking like this gate-all-around, or GAA FET. What's interesting is, in the transistor world, we're going down in dimension. We're going from not very good confinement in the channel to 2D confinement with the FinFET to 1D confinement with the gate-all-around FET. But in order to accomplish that, we're having to go 3D in the structure. And this is getting serious traction on industry roadmaps. And you can see how serious based on the number of authors that wanted to be on this paper by the IBM Alliance. Now, in order to replace the FinFET, you have to have more than one of these nanowires stacked, because the FinFETs are so powerful. So necessarily, you have to have 2 or 3 of these things stacked. In IBM's case, they call it nanosheet, it's a little oblong, but it's the same concept. And we know how to make this stuff. There's technologies that are available that allow us to make these. Very interesting paper this year from the IBM Alliance. Now, what really gets interesting is if you do go down this path, and you can make these stacked nanowires, here's an inverter, PMOS next to NMOS. There's nothing really saying that you can't go ahead and make more of these and stack the N over the P and get a Moore's Law node by folding in 3D space the transistors. And that, again, you see showing up on a lot of roadmaps called the CFET, the complementary FET N over P at the transistor level. Now, that's a one-time trick, like the contact over gate. But again, if you can do one layer of these things, who's to say you can't do more? And you can start to stack memory functions and logic functions, memory over logic. So there's a whole amount of complexity being investigated in this space that does present, hypothetically, a tenable path along Moore's Law with the current lithography. We're just not going to aggressively pursue the pitch scaling as much as integrate vertically. So what's interesting is it's not inconceivable that in some number of years, you could be working on systems with 4 kinds of 3D at the same time. So you could have interposer stuff, you could have the chip stacking, you could have wafer bonding, you could have transistor stacking, all forming some really advanced system that gets you to where you need to be. Now, the other topic is advanced memory. Out of all the different scaling stories, probably DRAM is the scariest in terms of its potential to continue to scale. And on top of that, we just continue to hit more and more of this memory wall, where we're paying a huge penalty in power and speed to access this DRAM. And even now, we're talking about the on-chip SRAM having some of the same problems. So the industry is really hungry for some kind of high-density, fast memory that can continue our path in this memory-intense world that we're finding ourselves. And you can see how hungry we are when foundries, which most of them are lining up along this MRAM path, when foundries are agreeing to dump half of the periodic table on their precious wafers, and then do it in this amount of precision. Those numbers in those layers are the thicknesses in nanometers. That's the challenge of MRAM. That's why you see it's not come along as fast as maybe a lot of people would like, but might be the best possible replacement for DRAM or SRAM potentially. Now, those two, the reason I picked those two is because then it gets even more interesting when you combine them. Now we're talking some really interesting stuff. And this is a paper by Stanford this year. It's an actual chip there. It's not just a simulation study. So this thing that I'm showing here, they've manufactured this with million sensors, lots of memory, and a compute layer with really high density interconnect. And this is specifically geared towards a machine learning application, so there's a lot of tricks in the machine learning architecture. But what you get with this, which, by the way, looks just like the image sensor I showed you, right? There's sensor, memory, buffer, logic. It's just that the sensors here are chemical. But when you do it this way versus a two-dimensional von Neumann CMOS, you're not talking about 50%, 80% improvement. You're talking about 100x, 1,000x. That's the Stanford claim is 1,000. So that's what's exciting about these two technologies being put together, is attacking things and getting these big jumps in performance. Now, there's also a CMOS layer on this that they don't show. So CMOS is our backbone of our industry. It will be there, but a lot of the differentiation going forward will be the stuff you can put on it. And I think we'll see actually a blossoming of diversity by this heterogeneous ability that we'll have. Now, it's not just some crazy professor at Stanford. Here's a recent announcement by DARPA. It's this Electronics Research Initiative. They have within that several different goals. One of them is very similar to what I showed you by Stanford, where you have non-volatile memory stacked in high density over logic. And they have similarly optimistic goals for this kind of architecture for these data-intensive machine learning applications. Now, you're going to have to play with your architecture and design to get there. So those are the two pillars there that I think most of you know and love in this room. I am a little bit more geared towards the third one, materials, and that's what I want to talk to you about now. So I want to talk about this, and I gave you a piece of art earlier, so some of you are wondering, is this going to be a Picasso? Is this a Moreau? Maybe an Escher? But it actually comes from this interestingly titled paper, Fundamental Materials Research and the Course of Human Civilization. And it actually makes a point that I agree with, that if we continue down this CMOS path with the power scaling story that we can expect, we're going to find ourselves needing more power than the planet can provide long term. And the only way to get off that long term is to come up with new materials that are fundamentally more efficient. And this particular picture is some research that this author did in multiferroic erbium manganate. And the term multiferroic is really interesting because it portends the possibility of an MRAM type memory that can be controlled with electric field instead of magnetic field and be very low power. Now, that got blown up in the popular press to even more bombastic headlines, so you'd be forgiven for not really knowing or caring that there's actual interesting technology down these things. And that is actually one of the challenges I want to get to discuss. And I want to pick one topic right now to show you that's two-dimensional semiconductors, two-dimensional stuff. We all know graphene. Graphene may or may not be, in the end of the day, a useful semiconductor device, but we continue to make a lot of progress with it. In this case, being able to manufacture it on full wafers instead of the Scotch tape way of doing it that won a Nobel Prize. Only, I think, 11 years ago. It's amazing how fast this has gone. Now, there are a lot of 2D materials. I actually talked about this last year a bit. Molybdenum disulfide is one of them. Here's an interesting circuit. It's a logic circuit with about 125 molybdenum disulfide transistors. It's a very interesting potential semiconductor material. But we don't have to focus on just the semiconductor properties. These two-dimensional materials can have really interesting optical properties. They can be magnetic. And in specific cases when they're magnetic, we can use them to control the electron spin as our information source and maybe go a lot lower power than using the electron transport. That's Spintronics. Now, what's interesting, there's actually another value of electrons called the valley, and two-dimensional semiconductors allow us to access the valley property of electrons potentially and use that for an even lower power way of managing information. Now, we can go ahead and let's invent some entirely new scientific fields with this stuff. Let's go ahead and do superconductors. With that, we can revolutionize quantum computing. We don't need to be selfish. We can use two-dimensional semiconductors to improve the manufacturing of other semiconductors. We don't have to stop with electronics. We can make things like smart paint. We can repair spinal cord injuries. We can detect cancer. We can revolutionize the field of speakers with something called electroacoustics. Very interesting, by the way, worth a look. We can solve the world's water woes. And last, we can maybe revolutionize the cost structure of electronics for things like the IoT. Now, I went back to electronics on this last one to kind of have you thinking about this for Rob's talk next. So keep that in mind with the materials side. Now, what was the point here? I know a lot of you are wondering that. The point is that all these press releases came out in less than a month's time this year. That's the amount of stuff that's out there. And a lot of it is hyped up, but there's a lot of real promise out there. The challenge is that we're talking about chemists and physicists and even biologists in a lot of cases that are another step or two removed from the semiconductor industry. They know they're making interesting stuff. They don't know our industry. They don't know what we need, what we can and can't use with our boundary conditions. This is going to be, I think, the challenge of the industry is this is where a lot of promise is to get off of that human civilization problem that we talked about with the first paper, is to adapt these kinds of technologies. But it's going to require a lot of people in the room that haven't been there before, from architecture all the way down into chemistry. I want to give you one example here at the end with work that we've done in ARM research. So we had a crazy professor come over. We like to do that in research. And he said, hey, I've got this really interesting material. Formingless, unipolar, quantum phase transition metal oxide. We said, okay, how does it work? So he goes over to the whiteboard and literally starts writing down quantum mechanical Hamiltonian operators. We said, time out, how does it work like IV? And it turns out he had made these things. They worked according to his theory. They were 5 microns in diameter. That's the capability of his lab. But the first 2 words of that title, by the way, mean it doesn't have the filament problems of an RRAM. And the last word means it's as fast as an MRAM. This is all high potential. But it doesn't work like either one of those. So in a circuit perspective, it's totally different, and you got to sit down and scratch your head about it. So we went ahead and did that. It looked interesting enough. So we went ahead and studied it, took a lot of circuit uniqueness and some hypothetical scaling into the nanometer regime where we'd care about it. And it turns out, yeah, might be interesting. So with that conviction, that amount of study, we went ahead and did the extra little bit of work to take it down into the nanometer regime, put it through the rigor of the boundary conditions of modern semiconductor manufacturing, the 300 millimeter wafers, weird etches, anneal conditions, the things that you have to deal with in modern CMOS. And it turns out the physics held up like it was supposed to. So it's interesting. There's a lot of arrows to the right. Those of you that work in this field know there's a lot of really long, gruesome arrows to get to the point where you can say, this actually will be an interesting memory. But the point is, this is a microcosm of the kind of problem that we necessarily need to face going forward. New materials are going to allow us to get places that we're not going to be able to go with the standard story long term, but they can't really be realized until we comprehend them in some way that's probably outside of our comfort zone. So that gets back to this idea of limbo that I talked about. There's going to be, we know there's so much activity in so many fields. I gave you just the 2-dimensional material example, but there's really interesting non-volatile materials. I showed you one example. There are combinations of new materials, and our ability in this industry to now pattern down to the nanometer regime that creates things called metamaterials that even break physics much further. So there's a lot of stuff out there that could really help us make these quantum leaps, those 1000x kind of numbers that I mentioned, but they don't look like MOSFETs, and they don't work like von Neumann computing. And in order to really realize it, you have to get up to the application level and abstract it up there, but it just doesn't work the way we do it. So that's a big challenge for us. And concurrently, we have the challenge of, none of this stuff is ready for prime time, obviously. It's in the press release stage, a lot of it. If we work hard and we do gate-around FETs and we do EUV, and now on the roadmap, there's potentially another EUV, high numerical aperture EUV. We put all the stuff together, maybe we can get to 2 nanometers. That's pretty far out there, but when you think about it, if we handle our 2-year cadence, we're talking about 6 or 8 years from now. And to give you an idea of time frames, MRAM, which we may start to see now, coming soon to a wafer near you, was invented 30 years ago. So that's the challenge that we have, is making the progress that we can make to extend Moore's law, and then helping the uptick of these revolutionary technologies at the materials level. I think we've got a whole lot of interesting work ahead for us as engineers, but I also think we have the system scaling opportunity that's far beyond what we actually can imagine with a lot of the interesting stuff that's going on outside in the physics and chemistry world.